after we got the reaction force at point A and point B, and then we need to draw the shear force diagram. So let's recall the relationship between shear force diagram, shear force with the distributed load. We have derived dV over dx equal to Wx. So this is meaning the slope of a shear force diagram is equal to the intensity of the distributed load. And we will also derive that the change between the shear force in 2 points is the area of that distributed load. So we have derived, if we just make an integration on both sides, we can derive delta V, the change between 2 points. If we see the point x1 to point x2 is Wx dx. That means the change of the shear force at the 2 points is the difference. The difference is equal to the area under that distributed load. So based on these two information, we can just draw the shear force diagram. So we start from the free end. So at the free end, the shear force is 0. Okay. So because the distributed load here is also 0. That means the slope here is 0. Okay. Slope is 0. And also then we move to the mid part of this segment. So then we find the slope of the shear force equal to the intensity of the distributed load, and the distributed load we see is going downwards. So going downwards is negative. So that means the slope is negative. So we go this way. Slope is negative, and slope here is smaller than slope here. So we go slope shape of way like this. We come to the point A. We come to point A. So we know at the free end the shear force is 0, and now we need to calculate the shear force at point A. As we know, the difference of the shear force between these 2 points is equal to, let's say, the area under the distributed load curve. So this is the area. We must calculate the area of this triangle. So if we want to calculate the area, we know from the free end to point A is 3 meters. So we need to know the intensity of the point A. Okay. If we see the intensity of point A is some, say the value is A. So based on the geometry information, so A to 27 is equal to free end to A 3 meter, and free end to B is 9 meter. Okay, just based on this two triangle. This is first triangle, this is the second triangle. Based on the geometry information will come out the A. Then we got A equal to, the A is the intensity of this point. So we got this result is line. So at point A, the intensity of the distributed load is 9 kilo per meter. Okay, after we know the intensity of this point, then we can calculate the area of this triangle. Then we calculate is 9 times 3 divided by 2. So this is the area. The area is 27 over 2, 13.5. So this is the area, 13.5. That means the shear force difference between point A and the free end is 13.5. Because we know this 0, this is definitely negative. So the difference is 13.5. That means the shear force here is 13.5 kilonewton negative. And then we look at here, we find that there is a concentric load at point A is a concentric reaction force 60.075 kilonewton, and it's going upward, so it's positive. So as we said, the concentric load make a sudden change on the shear force diagram. So we have a negative 13.5 plus positive 60.75. That means the shear force will increase to 60.75. So 60.75 minus 13.5 equal to 4725 kilonewtons. So let's say this is 4725 kilonewtons. So I join here. So then from this point, as we know the slope is the slope of the shear force is equal to the intensity of the distributing load. So intensity of distribution is also negative. So the slope is negative going down. And we know at this point, at point B, the shear force is 60.75. And if we say this is shear force over the point B, this shear force make this beam rotate counterclockwise. So based on the sign convention, we see if the shear force make the segment rotate clockwise, we say the shear force is positive. So this shear force make this segment rotate counterclockwise, and that means it's negative. So negative, we say negative 60.75 kilonewton. So from 40.25 kilonewton to negative 60.75 kilonewton. So the change is like this. Okay, the change is like this because the distributed load is linearly changed. So that means this curve is a quadratic curve. So then we got the shear force diagrams. We know there's some point on AB, the shear force is equal to 0. So because we know dm over dx equal to v, and based on this the relationship between the bending moment and shear force, we know the maximum bending moment is happen at v equal to 0. So in next video we will talk about how to come out this point and how to calculate the maximum bending moment.